So again, sorry, I made a mistake here. This is not the number, this is degrees of freedom, so which is n minus 1. And so this would be with 2 measurements, this would be 3 measurements. 12.7, 2 measurements. 3 measurements is going to be 4.3. 307. And so that's what we'll use here. And so I need to recalculate this one. So can you redo your calculations and then tell me what you get? $4.307 times 20 divided by square root of 3. 49.7. 49.7. So student 1, lambda 95, 49.7, so roughly 50. Okay, so this is plus or minus 50% sulfate. What did student 2 get? Tell me when somebody has it. 6.1. 6.1? Okay. So student 2 would be 67 plus or minus 6% sulfate. We'll just round it to the same number of decimal places as the other. And so student 2 has a much narrower range, with a much tighter standard deviation. And so when we look at it, it's just looking at the spread of the results. So one measurement here, one measurement here, another measurement here. This would be student 1. So they're going to have a very broad distribution. Whereas student 2, you have one measurement here, one measurement here, one measurement here, very tight distribution. And so you'll have to do the same thing for your sulfate. You'll get 3 sulfate percent masses and then just calculate the standard deviation. And then use the equation there with the t value from the table to get the 95% confidence. And then report your result with a plus or minus lambda 95. Okay, any questions on the calculation for the sulfate lab? All right. Well, today what I want to do is do a little bit of catch-up as well for Chapter 8. And then the computer lab is quick. We're just making one plot So it doesn't take very long. Today's. And the calculation is also very quick. All right, so last time we were talking about making a hydrogen lamp, you know, and hydrogen was supposed to behave as a black body emitter. This is our hydrogen lamp. Hydrogen atoms are supposed to be a black body emitter because the hydrogen atoms just consist of a proton in the center and an electron. And can this electron achieve any energy? So if we think about the electron, we can think of the energy as being kinetic energy and speed. So can this electron achieve any speed? Well, it depends on how big of a kick we give it. You know, there's some collision or something in the lamp. But we decided, well, yeah, we can give it a little bit of a kick that will give it a little bit more energy, right? A little bit more energy, a little bit more. And so eventually what we're going to see, or we can get a little bit less energy here. And if this is moving faster and faster, it's going to move farther and farther away from the nucleus as it gets faster and faster, right? But basically, we should be able to excite it, you know, with infrared, just a little bit. Or we should be able to excite it with visible. Should excite a little more. Even UV. We should be able to excite this UV energy. Is the electron going to stay out there at high energy? No. Eventually, that electron is going to drop back down in energy and emit. It should emit. In fact, it should emit the full rainbow of colors. So we should get nice white light from a hydrogen lamp. You know, just like molten iron. Right? Molten iron's got electrons. Those electrons can get excited. Molten iron emits white light. Okay. And so the hydrogen lamp should emit white light as well. The problem is that it doesn't. You know, this is the emission spectrum of the hydrogen lamp. And so you see, you know, 390, look at the red. Most of the red region's black, which means that there's no light being emitted there, which means the electrons aren't being excited here. It's not until you get to 656.3 nanometers that you see a line. And so what we call this is, when we see a spectrum like this with black regions, those black regions are forbidden regions. And so since there's no light being emitted here, these are forbidden. That means the electron is not allowed to have these energies here. These are all forbidden. And then once I get to 656.3 nanometers, then, electron is allowed. Here, this is allowed. And so let's say that amount of energy kicks the electron up to here. And so the electron's allowed here, but it's forbidden here. So this would be allowed. This color is not matching. This is allowed. This is forbidden. Okay. And then look at this. This is all forbidden here. And so there's a huge range of energies that are all forbidden. And then all of a sudden we have an allowed energy here. There's allowed. There's just one specific energy here that's allowed. And then forbidden energies. And then allowed. And on and on. So we have a huge range of forbidden energies, and then we have some allowed energy out here. And so in terms of thinking in terms of speed, this is it. The electron cannot get any speed it wants or travel any speed it wants. The electron can travel, let's say, at 25 miles an hour, but it cannot travel, let's say, at 25.1 or 24.9. Those are forbidden. And then there's a big jump. Let's say now it can travel at 60 miles an hour, but not 55, not any of the others. And then there's another big jump. And so the electron can only travel at certain speeds. Well, this goes against classical physics because the electron should be able to travel any speed it wants. I mean, what's stopping it from slowing down a little bit or speeding up a little bit? Physics predicted that hydrogen should act as a black body because physics predicted that the electron should be able to travel any speed it wants. You know, it depends on how much energy you give it. You give it a little bit more energy, a little bit faster, a little less energy, a little slower. But there should be no forbidden energies. And so classical physics predicted that the electron should be a good white light source, a good black body emitter. But what we see here is that it isn't. You know, if you look at adding red, green, blue, and violet lines together, it doesn't look white at all. It looks purple. You know, and this would make an awful reading lamp. And so the question was, why are there allowed energies and why are there forbidden energies? Well, the first thing is there a pattern to this? And it turns out there is a pattern to this to these numbers. The empirical equation that fits this is the law. You know, it's the Rydberg equation. Law. And the Rydberg equation says that we see a pattern in the energy changes here. When we look at the energy changes, you know, which would be this 656.3 nanometers, is delta E is going to equal h nu, which is equal to hc over lambda. The energy changes are going to come from, you know, how this red photon is being emitted. The red photon is being emitted because the electron's at higher energy and then drops down to lower energy. This is just E of the photon. Well, this is going to equal, delta E is going to equal E final minus E initial. Or E is just the energy of the electron, which is going to be given by this, is minus R sub H over 1 over N final squared minus 1 over N initial squared, where N is equal to 1, 2, 3, dot, 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 all the way to infinity. And so it's an integer from 1 to infinity. So this mathematical equation fits this. And so what we see is this. That we have these quantized energy levels. They're quantized energy levels because they're going to depend on steps. And so quantized versus continuous would be like this. You know, we have the first floor, the second floor, third floor, like this, versus continuous. And so the quantization comes from here, n equals 1, 2. But it cannot equal 1.1. That's forbidden. Continuous, we could have any value, you know, of n. N can equal 1.1, etc. Be continuous. And so the electron cannot have a continuous energy level like predicted from classical physics. Classical physics predicted it could have any energy it wants, therefore it should act as a white light source. But what we see is we see what's called a line spectrum. They're distinct lines. Each line is allowed energy. Allowed. And that's going to be quantized versus continuous. If this were continuous, what we'd see is a full rainbow of colors, from red all the way to violet. You'd see the whole rainbow. So this is the law. Then what's the hypothesis? So this is just the scientific method. In fact, this chapter is about the scientific method, and so this is why we're doing a little bit of history here. The scientific method starts off with what? The scientific method started off with hypotheses. So what did they hypothesize? They hypothesized that. What did they hypothesize? They hypothesized that they're going to see 4 lines in the hydrogen atom spectrum, and that these 4 lines are going to be red, green, blue, violet. And the red line is going to come out to 656.3. Is that their hypothesis? Did they hypothesize that hydrogen is not going to be a black body emitter? No, they hypothesized that the hydrogen is going to be a black body emitter. That's the hypothesis. The hypothesis failed. The scientific method doesn't start always with a hypothesis. You know, did somebody all of a sudden come up? I had a dream that classical physics, which predicted energy to be continuous, is wrong? The reason I bring this up is because everybody, you know, I say this because nobody wants to listen to me about the scientific method. Everybody learns in biology that the scientific method begins with a hypothesis and then you test the hypothesis. But it depends on what type of science you do. With certain types of science, it's this very, very difficult, extremely difficult to do. You know, to come up with a hypothesis. Who would have hypothesized this? Tell me. Who would have hypothesized this observation? This is very, very difficult. And so in chapter 8, they didn't hypothesize this. Nobody hypothesized this because everybody hypothesized that that they're going to see a rainbow of colors. That was the hypothesis. And so this scientific method doesn't begin with hypothesis. But this scientific method began with observation. What we have is we have this unusual observation. You know, why isn't hydrogen acting as a black body? And then what do? Do we automatically go to a hypothesis? No, we look for patterns. The pattern that was found is there's a pattern. There's a number pattern here. The number pattern fits this equation here. It's this very simple equation where r sub h is just some empirical constant. R sub h, you just get this is some constant times this, but the number pattern is this. And so it fits this number pattern, but then what comes next after this? Well, this turns out to be a law because it's a very consistent number pattern. Actually, this number pattern was able to predict that beyond the red in the infrared region, we'll also see the same number pattern. And actually, with an infrared spectrometer, you can observe the lines. There are infrared lines here. And the infrared lines here fit this exact same pattern. And then out in the UV, although you don't see it, but if you have a UV detector and you do UV spectroscopy, you'd see UV lines out here that fit this same pattern here. They named these differently. They named they named it after the discoverers, but the math is exactly the same. It's the same equation, but they gave names. Balmer series to Balmer, who discovered one, Lyman to another, and I think Rydberg for the other. But you don't have to know the names. It's just the pattern holds. So that's why we call it law. But and when we use that law to make predictions, but once we have the law, then what do we want to do? Here's where we come up with if we have a law like this, why does this pattern follow this law? Then we come up with a hypothesis, right? Do you guys remember this from first week? We come up with a hypothesis. This is the hypothesis. The hypothesis is that energy is not continuous. The energy for an electron is not continuous, at least in a hydrogen atom. It's not continuous. It's quantized. Quantized means that not all energies are allowed. If all energies were allowed, we'd see a rainbow. We're going to have forbidden energies and allowed energies. The gaps here. These steps aren't necessarily even. The steps aren't even. The steps. Actually, I should draw the steps more accurately. Initially the steps are large, and then the steps get smaller as we go on. Like this. We'll look at it later. And so the steps aren't the same size. And so this is a hypothesis, and so which led to the theory. The first theory turned out to be incorrect, and so this hypothesis led to the Bohr theory. Bohr theory was proven wrong. But we'll talk about it because it's very simple. What Bohr hypothesized and what the Bohr theory developed was that the electrons orbit the nucleus. And so this would be a Bohr orbit. The first orbit is what we call the n=1 orbit. And the energy of this orbit we can calculate. The energy for the orbit is calculated as minus r sub h over n squared. R sub h, the Rydberg constant, is like 2.179, 10 to the minus 19 joules. I don't remember. Let me look it up. 10 to the minus 18 joules. So even though the Bohr theory turned out to be wrong, they still made stamps after him. Niels Bohr, atomic theory. Here's the energy of the electron. These are allowed energies. Any other energy is forbidden. And so So an energy with n equals 1.1 is forbidden, 1.2 is forbidden, 1.23 is forbidden. In fact, all these energies, until we get to the next energy that's allowed, the next energy that's allowed is going to be n equals 2. Now, it's kind of funny here. So this would be the next allowed energy. So we could calculate these. So the first one is going to be, this first energy is going to be minus 2.179 times 10 to the minus 18 joules. Now, a negative energy, well, how can I have a negative energy? I'll talk about that in a minute because it depends on what zero energy is. And so you'll see what zero energy is in a second. And so the next allowed energy is n equals 2. Well, it's going to have higher energy, so it's going to have an orbit with a larger radius. It's going to be moving faster. The radius we can calculate. The radius is equal to basically it's equal to 0.54 angstrom divided by n, or not n, not divided by, sorry. It's times n squared. And so we call it R0, R sub 0 times n squared. And so the first one is like 0.54 angstroms or 54 picometers. The second one would be 4 times that, which would be, this would be R2, so R1. And so this is going to the radius of this orbit is going to be 2 times that would be, 4 times that would be 216 picometers. Or angstroms, remember angstroms is being in banded. It would be 2.16 angstroms. The energy for this, what would the energy for this orbit be? Well, if an electron were in this orbit, then it would be 1/4 that energy. So minus 2.179 times 10 to the minus 18 divided by n squared, which is 4. 1/4. All right, so this is allowed. This is allowed. And these energies here are forbidden. And this goes on. What's the highest energy that's allowed? The highest energy that's allowed is n equals infinity. At n equals infinity, then what's the energy of that orbit? Well, it's going to be minus 2.179 times 10 to the minus 18 divided by infinity squared, which is going to approach what? 0. And so this is why the energies are negative, because the highest energy allowed is 0 joules. And what is the orbit of that? Well, R infinity is going to equal R0 times infinity squared, which is going to be infinity. In other words, the electron is completely knocked off the atom. We call the electron ionized. If the electron's here, it's ionized. If electron is here, it is ionized from the atom. So you have an H plus an electron. And so when we look at the energy level diagram, this is what the energy level diagram looks like of the quantized energy states. The energy level diagram, based on these transitions of forbidden and allowed, we have the highest energy, E infinity. E infinity is at 0 joules. And we have the lowest energy, E1. The lowest energy is at minus 2.179 times 10 to the minus 18 joules. And then we have an infinite number of levels here. So E2 is 1/4, and then E3 is 1/9, and then E4 is 1/16. And then what happens is these start to, we got to draw an infinite number of lines here. These start to get closer and closer spaced. And so as we get closer to infinity, there are a lot of lines in here. And so it starts off with bigger jumps. But as we get higher and higher in energies, those gaps become smaller and smaller, and the jumps become much smaller. So out here we might be at E 100, and then E 1000, and then E at 10,000, etc. All right, so this is the Bohr model of the atom. So the question comes up is, why are there forbidden energies? So, like, why can't the electron orbit here in this forbidden area? And what was the reason for that? Well, the reason for that was that it can't. The electron can't orbit here because it can't. Does that sound like a good reason? No, you know, these are so what we call the postulates of the Bohr model. The postulates are, you know what a postulate is? A postulate is taken without proof. And so we just take it without proof. It can't because it can't. Those are forbidden. That's it. All right, so if you accept that, that's fine. What the Bohr models was pretty successful at is predicting these transitions. And so if we look at the equation here, this is what we got. One thing Petrucci doesn't like is he doesn't like negative signs. So if you compare Petrucci's equation to my equation, Petrucci's equation is positive R sub h, but what he does is he flips initial and final. What I did was I just left it at minus R sub h and then just left it final minus initial. But what Petrucci likes to do is get rid of that negative sign and then do initial minus final. It's the same equation. You could use whichever one you prefer. I always like to do final minus initial. But Petrucci will change it. Initial minus final or final minus initial depending on which one gives a positive equation. All right, so this is it. So I said that these lines all fit the same equation, and they're named after the discoverer of it. And so we can take a look at mapping this out, the energy level diagram for the hydrogen atom here. The first step is going to be a big jump, you know, because when we go from E1 to E2, it's going to be the biggest jump. So we're just looking at the beginning of the table here. E1 to E2, and then E2 to E3 smaller, E4 to E5. Look at E5 to E infinity. We have to draw an infinite number of lines there. It's going to get crowded, right? Well, the electron can get excited. Normally, hydrogen has one electron. That electron is in the lowest energy state, what we call the ground state. And then if you excite it, you can excite it to many different levels. So if we have a lot of hydrogen atoms, not all the hydrogen atoms will get excited to the same degree. You know, some will get excited to n equals 2, some will get excited at higher and higher energies. In fact, what we're going to see is we're going to see a Maxwell-Boltzmann distribution in the population of the energy levels because the energies follow that type of distribution. That is, some hydrogens will be high energy, some will be lower energy. Do you guys recall the Maxwell-Boltzmann distribution? Thermal distribution? In other words, when we look at the population, the greatest population will be in the lower energy states here. Depending on the temperature is going to shift the distribution, but it's this kind of curve, bell-shaped curve. We usually look at it this way, with a higher energy tail. Do you remember that? And so this is going to be the population. So if I have a lot of hydrogen atoms, the greatest population of electrons is going to be around here, depending on the temperature. And so what's going to happen is I'm going to start seeing a lot of lines in the spectrum because those electrons don't stay excited forever. So if an electron goes from the n equals 2 to the n equals 1, it's going to emit energy. We can calculate that energy using the Rydberg equation here. This energy turns out to be in the UV. And so this will give you an ultraviolet line. In fact, all the transitions, the n at the ground state here, are in the ultraviolet. But it doesn't have to drop all the way to the ground state. It could go to the second floor. If it goes to the second floor, then we get the visible lines here. And so going from the third to the second results in the red line that we see in the spectrum. Going from the fourth to the second results in the green line. The fifth to the second results in the blue line. And the sixth, which is not shown here, the sixth to the second results in the violet line. These colors are screwed up, but it doesn't matter. We can calculate those. And so we see this. This line comes when the electron goes from n equals 3 to n equals 2. And this wavelength we could calculate using the energy that we get from this equation here. This line comes from the transition from n equals 4 to n equals 2. This is the green line. This one comes from the n equals 5 to n equals 2, which is the blue line. And what was not shown on that was the n equals 6 to n equals 2. This would be the n equals 6 to n equals 2 transition. When the electron goes from the 6th to the second floor. This is just how to measure it. We did absorption spectrum, where we shined white light on a sample here and see what colors are absorbed. This is emission, where we excite the sample. And so emission results in going from higher energy to lower energy. Absorption results in going from lower energy to higher energy. It absorbs light rather than emits light. The ionization energy is a common calculation that we do. The ionization energy is just given as this. It would be an absorption. And so to ionize an electron, we take an electron in the ground state and then promote it to the n equals infinity state. And then it's completely ionized. And so how much energy does this cost? Well, the amount of energy that's going to cost is delta E is equal to E final minus E initial. Or using the Rydberg equation, delta E is equal to minus R sub H, 1 over N final squared minus 1 over N initial squared. And so when we do that, well, we'll get minus R sub H. 1 over N final is 1 over infinity squared. Minus 1 over N initial squared is 1 over N 1 squared. And so this is going to be 0, and this is going to be negative 1, so it just comes out to plus R sub H. And so the ionization energy for hydrogen is 2.179 times 10 to the minus 18 joules. And so that's it. .179 times 10 to the minus 18 joules plus. That's joules per H atom. Now, if I have a mole of H atoms, then I'd have to multiply that by Avogadro's number. And so if I have a mole of H, let's go ahead and do that. It's going to be 2.179 times 10 to the minus 18 times 6.022 times 10 to the 23rd gives us 1,312,000 193.8 joules. So 1,312,193.8 joules per mole. Well, that's a cumbersome number, so we'll just call it 1,312 kilojoules per mole. And so to ionize a mole of hydrogens would cost you a minimum of 1,312 kilojoules. That would be the ionization energy. Well, theories have to do two things. What do theories have to do? I'm going to stop soon. Theories have to, the theories have to be a fundamental description. Well, this is the fundamental description: electrons orbit, etc. They have to be a fundamental description, and then they have to predict new, unforeseen results. And so let's predict the helium. And so Bohr failed because it could not predict atomic spectra for anything except one electron species. So it failed for helium, but it was a success for He+, which is one electron. It failed for lithium, but it was a success for lithium 2+. It failed for beryllium, but it was a success for beryllium 3+. So anything with more than one electron, the Bohr failed. The Bohr equation had to be modified, etc. If we have a one electron species, then the energy is modified in this way. The energy is going to equal minus R sub h over n squared. But we have to modify this by putting z in there. And so there's going to be a z term in here, and that's called z squared, where z is the number of protons in the nucleus. And so that's what we see here. This is the modified version of the Rydberg for one electron species. But if it fails for all these, which is most everything, then it fails. And so the Bohr ultimately failed. The Bohr model failed. These successes weren't enough. And so the Bohr theory failed. It wasn't a complete failure because the whole idea of quantized energies continues. But most atoms contain more than one electron, and so we can't use it. And so this was replaced by the modern quantum theory. And so it was replaced by quantum theory or quantum mechanics. So quantum we heard before in Bohr, the energy levels are quantized. That is, there's forbidden and allowed. But this is a little different, this quantum mechanics. And so let's talk about quantum mechanics briefly. Quantum mechanics, there are two important developments that led to. So what quantum mechanics did is retains from Bohr, retains the whole idea of quantized energy levels. the empirical equation still works. Retains quantized energy levels, but adds one this de Broglie wave particle duality of matter. Okay, so we're going to have another lambda here. There are too many lambdas. This is going to be lambda for matter, not lambda for light. It is not equal to lambda for light or electromagnetic radiation. And so matter is going to have its own wavelength, which we can get from the de Broglie equation. Jump forward here because we have a slide for that. This is de Broglie here. And what he said is small particles of matter may at times display wave-like properties. And we have an equation for that. Broglie. And this is his equation, that the wavelength of matter is equal to h, which is Planck's constant, divided by p, which is momentum. Momentum is given by mass times velocity. And so lambda of matter is equal to h, Planck's constant, divided by the mass times the velocity. And so, like, for example, a baseball would have wave properties. A car, let's have and then 2 is the Heisenberg uncertainty principle. We add the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says this: there's a fundamental limit to the determination of the position of the electron and the energy of the electron. Energy being in terms of momentum here. In knowing those two values. And so what that means is you cannot pinpoint the position and the energy simultaneously. This is particularly important for the electron. And so it's very difficult to pinpoint the electron's position and its energy simultaneously. You can pinpoint the position, but that leaves uncertainty, the uncertainty given by this delta. And so if delta x shrinks, delta p must grow. And so if we pinpoint the electron, we want to pinpoint its position. Delta x is going to shrink, delta p grows. That means we don't know the energy very well. Or we can pinpoint the energy. If we pinpoint the energy for the electron, delta p shrinks. That means that the position uncertainty grows. What do you think we want to pinpoint? Do we want to pinpoint the position of the electron, or do we want to pinpoint the energy of the electron? It turns out we want to pinpoint the energy of the electron. We want to know what is the energy of that electron. And so what we do is we shrink down the uncertainty in the energy, and that means the uncertainty in the position grows. It's not infinitely large, because h, Planck's constant, is small. It's 10 to the minus 34. Divided by 4, pi is 3.14. And so it's not huge. The uncertainty is not huge by any means. 10 to the minus 34 is not big, right? But it has implications for the electron in particular. So we add the Heisenberg uncertainty principle, that is uncertainty in position and uncertainty in uncertainty in position and uncertainty in energy is got to be greater than or equal to some constant here. We factor these two things in, and then we get the equation for the energy of the electron. And so quantum mechanics is based on this equation. This is the Schrödinger equation. The Schrödinger equation is tells us the energy. It's kind of a funny looking equation. Let's just end with this Schrödinger equation here, and then we'll take a break, and then oops, did I not get that? The Schrödinger equation isn't even shown here, but it pretty much tells us the energy, and it tells us about the position. Not just X, but this. And it's kind of a funny looking equation, you know, with these symbols, these mathematical symbols. But those mathematical symbols are just abbreviations for something more complicated. But essentially what we're going to get from this equation is the energy and the position. Okay. And so this would be the equation itself. And so and the end result is this. The positions are given by orbitals, not orbits. The orbitals are given the symbol psi, and the orbitals are probability functions of finding electrons in a volume of space. Because, like I said before, we want to pinpoint the energy. And so here we pinpoint the energy of the electrons. Here we pinpoint, if we pinpoint the energy of the electrons, then we can't pinpoint the position. And so the positions are going to be given by these. The probability of finding electrons in a volume of space is actually given by psi squared. And psi is an answer to the, and so what we get from the Schrödinger equation is the energy and psi. Psi is going to be related to this. Okay, psi is what we call an allowed state for the electron. An allowed state for the electron is both the energy and its positional state. And so this is an allowed state for an electron. It turns out that there are a lot of allowed states for an electron, lots. And the allowed states for the electron, since there's so many, in fact, for a hydrogen atom, there are an infinite number of allowed states. Well, if the hydrogen atom has an infinite number of allowed states, then that means it has no forbidden states? No, it means it has an infinite number of allowed states and an infinite number of forbidden states. Okay, it's weird. And so what we say here is that psi, the easiest way to deal with psi is not individually. The easiest way to deal with psi is by looking at it mathematically as a equation. And where did I put that psi? Sorry, you can use inside psi, we're going to have different parts. We have a y part and an r part. And these are the mathematical equations for individual answers to the Schrodinger equation. But it turns out that the psi is a mathematical function. Mathematical function. It's a mathematical function that depends on three variables, n, l, and m. These three variables have restrictions for allowed. And so allowed n values are restricted to 1, 2, 3, ... to infinity. Therefore, an n equals 1.1 fails the Schrodinger equation, and it's not an answer to the Schrodinger equation. And so n equals 1.1 is forbidden. It's forbidden because the math doesn't work out and the Schrodinger equation fails. But an n equals 1 is fine, n equals 2 is fine, etc. L is going to vary from this. We're going to go from 0, 1, 2, ... to a max. And so it's going to take on all values to a max of n minus 1. And so the biggest L value we can have is n minus 1. And m is going to take on all values from this, minus L to minus L plus 1, ... through 0, ... through L minus 1 to plus L. Takes on all values. These are allowed. Everything else is forbidden. Allowed. Everything else is forbidden. All right, so what we're going to do is we're going to talk about the two additional discoveries or developments that led to quantum mechanics, the de Broglie and Heisenberg in more detail. And then we're going to talk about the Schrodinger equation and the answers to the Schrodinger equation, the answers being the allowed states for the electron in more detail. And then we're just going to apply the Schrodinger equation to different atoms and ions. Okay, so I'll stop here and then